There we go. All right. The final will be, as I was saying, it'll be an asynchronous part that'll go from anytime, I think between 8 and 6, you can take it. And then the synchronous part will be live with me from 7 to 8:40, and you'll tune into Zoom and take that part of it. So I think that's a little better, I think, than the past when we've had one big long final for 3 hours. So, but that's the plan, almost to the end here. Okay, I want to mention the quiz. If you haven't checked already, the quiz 4 and 5 are graded. So the only thing I've left to grade is your homework 6. So I should hopefully get to that soon. But here's the solution. I did it in Excel. Either way is fine. One thing I noticed is some of you assumed that this 68 millimeters up here was just for this little red area. But remember that those little lines I put in there just to delineate the actual shape. So the 68 was for the entire length. Otherwise, the answer for IX was 1.9 million, and for IY is basically 1 million. So a lot of you got real close. I'd say that most of you did really well on it. The only mistake I saw was sometimes your D values were off. So that's something that I would just check on, make sure you have that, because this quiz is going to come back, not this quiz, I'm sorry, but this subject is going to come back on the final. High probability that you will have a moment of inertia centroid problem on the final. And so if you can master the concepts, then you'll be that far ahead. And the geometry won't be any more complicated than something like this. Maybe we'll add a half circle or something, but it won't be anything super tricky. So any questions? All right, I assume you can all hear me. I haven't heard anyone yell they can't, so I'll assume that's correct.
I can hear you.
I want to talk a little bit more about zero force members. Now, zero force members, the idea, just to review in case that you have any questions on what they are, but remember that the rules are that two members, if you have two members and neither are collinear, meaning they're not in a straight line, then they're both zero force. Or if you have three members and two are collinear, that means the third is a zero force. And so the second bullet is the most common that you'll see. And of course, the caveat is that there's no applied force or reaction. So that's what differentiates. So if we look at the first one here that has A, B, C, D, E, well, actually, I guess they both do, but the triangle on the right, and you see the load P going down. Which do you see right away? Which members are? Do you see what? First off, what are the zero force member or members in this one? Any volunteers?
BE and CE.
Pardon me.
BE and CE.
B D. You said
Oh, are you talking about the left one or the right one?
left one.
Oh, okay, then BD and CD.
Good. Thanks. I thought. Oh, sorry. I was trying to use my headphones, and that's why he came through my other speaker. You guys can hear me, okay? Can you?
Yeah, we can hear you.
Yeah.
What is that? Okay. So then the right one, I think you answered that one too. Is that the right one? You have BE and CE. So that's good. I mean, these are somewhat simple, but I think that once you see a few of them, you'll see that there's kind of a consistent way to see them. As long as you have, I would say there's three joints and there's no forces, then that's a big indicator. And don't be confused if one side doesn't meet the criteria, but the other side does, because both sides have to. So obviously at E, there's four members and a reaction. So you couldn't garner any information from that, but you can from the other side. Okay, well, good. Any questions on zero force? All right. Okay, so I want to just look at this quick method of sections problem here. You guys have probably maybe have done it or done your method of sections and you completely understand it, but let's just go through this one real quick as kind of a review. Set my camera. So here we have this. This should look familiar. It's what we looked at last week, and only last week we did method of joints. And so here we're going to do method of sections in the same one. So you recall that EY and AY, the reactions were 3,500 and 7,500. And so that's the first thing you're going to do most of the time on trusses is find those external reactions. So let's go ahead. Oops, sorry. There we go. All right, so there's our diagram. All right. So what we have is and I think the thing with method of sections is where and when do you make a cut? And so when you make your cut, you typically want to, it's based on what members you're looking for. So in this case, what are we looking for? We're looking for CD and we're looking for FC, and it doesn't matter if you call it DC or CF. And then we're looking at FG. And so if we make our cut, then that's going to go through like that. And so when we make our cut, then we end up with something that looks like this. Okay. So now when we do our cut, we ignore everything to the left of the cut. Now we could have cut and then ignored everything to the right of it, and that would work too. In which case these arrows would be reversed. C would still be there. The arrow would be pointing this way. C would be pointing that way. G would be pointing that way. Now, it doesn't mean necessarily that that's the direction of the force. It's just that's how we would identify it. And then this would all be dotted out or solid. But by doing that, we eliminate, by doing it this way, we eliminate this reaction, that force. We don't have to deal with any of it. So then all we have to worry about is this 3,500, which I think makes things easier. So if we're going to solve for that, then we have two ways we can do it. Well, there's several. There's no one way that's perfect, but this one is just shows that you only have one member that has a y component. So you could sum the forces in the y direction and get that one. And so if we did that, we could easily find what FG is. Another method would be to sum the moments about F. If we did that, then we could find what CD is. And then once we had those and those, we sum the forces in the X and we find that. So let's do that. So we'll start with, we'll sum the forces in the Y to 0. And if we do that, we know that we have 3,500 going up. And then we have, the way I've drawn it, I have minus, and remember this is a 3, 4, 5 triangle, so 4/5 is going down. So minus 4/5 of CF. And then that gives me 0. So if I solve, I get CF or FC, whatever we call it, 4,375 pounds. Okay. So that's pretty straightforward. So we see that. So then the next step is to then sum the forces, sum the moments about F to 0. And if we do that, then we basically get rid of this one, and we can solve for that. And you can see that makes things actually fairly easy, because we know that this is a distance of 6 and this is a distance of 8. So what do we have? We have a 3,500 pounds, and that's times a distance of 6. And then the way I have it drawn, I have it going away, so it would be plus, which we could probably surmise is not right, DC or CD, whichever, times the height, or times the height, which is 8, and that gives us 0. So we end up with DC equals negative 2625. And so we know that we were incorrect that CF, I'm sorry, I should put that, that's in compression. And DC, since I got it negative and I assumed it was tension, that means I was wrong, it's in compression. So it's DC or CD, I should say, is 2625, and that's in compression. And then last, sum the forces in the X to 0. And then that's just going to be CD plus 3/5 of CF minus FG. All right. So you have 2625 plus, and 3/5 of CF actually ends up being 2625. And that all equals FG. FG equals 5250, which you may remember was 5250 was this value. And last week when we did this side, we found that HG was 5250. And since this is a zero force member, we knew that GF and HG had to be the same. Okay. All right.
Professor, I have a question.
Yes.
Didn't you say, like, for CD, when we found out it was negative, to use that negative value to solve the rest of our equations?
In the, well, is assuming that I had, that's only if I had multiple equations and multiple unknowns.
Oh, okay, but since it's just summing the forces, we can just use the positive value.
Well, you use the value of what it really is. So for example, because what I've done is I've accounted for the fact that this is positive, meaning it's pointing to the right, because originally when I summed the moments about F, I assumed it was pointing to the left, but I was wrong. So if it's pointing to the right, that means that when I sum the forces, that means if it points to the right, it's positive. Right? So
okay.
Yeah, so I guess there's two ways that if you're solving two equations, two unknowns, and you end up with a negative, then you're right. You want to plug that negative back into your equation and solve. And then if the other answer you get is positive, then that means that one was correctly identified. But if you're doing something where we don't have multiple unknowns, we're just solving for one unknown at a time. And once we realize what the correct one is, we can go ahead and plug that in when we sum the forces in the X. Because really what we're saying is we know we have 2625 going this way. We have 2625 is the horizontal component of that. Therefore, this plus this has to be the 5250 going to the left.
Okay, I got it now. Thanks.
All right, sure. Okay, let's go back. Okay, so now this is a frame example. And so the frames, as you work on these, you'll probably notice that actually, can you see, are you seeing my screen, or are you seeing the, you're seeing the PowerPoint, aren't you?
It's the PowerPoint.
Okay, good, thank you. So when you look at a frame example, there's a couple of things you want to think about when you're doing these problems. Is normally with a frame, you can find the reactions. If you can find the external reactions, in this case, it'd be O and B, then you would. But then the caveat is that it depends if you need them or not. So you want to look at each frame problem is unique in the sense of what it's asked for. So what in terms of what you're being asked to find. So for example, in this one, you're calculate the forces supported at pin B. So all we care about is what the reaction is at B. Now, because B is a pin, we know it's going to be either an X, BX or BY, and that's it. So we want to look then at the structure and say, well, what is unique about the structure and what can we eliminate? So typically frames will be, if you can find the external reactions, you will, and then from there, you'll generally take them apart. And that's how you solve frames consistently. And you'll see that in the examples in the lecture and also in the couple examples I'll do here. So now if since both pins O and B both have an X and a Y reaction, then, and they're not at the same height, we really can't solve. We can only, they're indeterminate at this point. So, but if we look at the thing, we notice that OA is a two-force member. And that's important to recognize those because since OA has no external reaction and it's only held by 2 points, it's a two-force member. And you can probably see from that how we would go about solving this. Because if we look at, let's go ahead and look at our example. So here we have this, and so I'll go ahead and I'll draw. I know that I have, and I sent you this image, so you guys should have it if you downloaded it. OY, OX, and then we have A up here. We know it's 0.6. We know about here. We have our 200 Newton meter moment. We have 0.4 and 0.4. And then of course the radius of this was 0.4. All right. So then of course we have this and we have this. So BY and BX. So we just want to find BY and BX. And that's all we care about. So how would you do this problem? What do you think? Could we, what if we drew just this piece here? Yeah, let me do it with them. Okay, so not super pretty, but we know that there, OA, OA is going to be pointing in that direction. We know that that's going to be 45 degrees because it's a quarter circle. And since we know this distance and we know this whole distance is 0.8, where the moment is really doesn't matter because it's a free moment, like all moments. So we have BX and BY. All right. So what are we going to do? Then we can simply sum the moments about B to 0. And if we do that, that's going to allow us to find OA. And then once we find OA, we can just sum the forces to get that. So this is very much like a chapter 4 problem. Probably looks like it, and there's a lot of overlap in the frames. So if we go ahead and do that, what do we have? We have root 2 over 2 times OA. And we know that now root 2 over 2 we know is good for both of them. So we have one piece going this way and one piece going that way. But both of them cause a clockwise moment, don't they? So I'm going to make this positive. So clockwise is going to be positive. That's my convention for this. So I have root 2 over 2 OA times 0.8 plus root 2 over 2 times OA. And that's going to be, actually, I didn't need to put that in parentheses. Sorry, my chicken scratches. 2 over 2 times OA. And that's going to be times 0.6. So that's the two versions. And then minus 200 Newton meters, and that equals 0. So OA ends up being about 202 newtons. And then if we go ahead and sum the forces in the X, then we can get the balance. So if we can almost see this by default, though, the way it's going to line up is that all of the force going up is going to be basically 202 times cosine of, or sine of 45, and all the forces going to the right are going to be cosine 45, which is basically the same thing. So bx and by end up being the same. So we end up with bx, if we sum the forces in the x, we end up with bx plus root 2 over 2 OA equals 0. And same thing, by, so the force on the y are 0. We end up with by plus root 2 over 2 OA equals 0. And so, and the only difference is what we find is that because this is going up and to the right, bx and by are going to the left and down. So bx, and this is how you want to put your answers. You want to say bx, by, and you'll put your answer here, negative 142.9 and negative 142.9. Now, either put them as negatives, which would then imply that they're this way and down, or you can just draw them positive with arrows. So either way, but I find that if you put arrows, that tells you. Now this might seem counterintuitive to put a negative in front and then that, because that would almost imply it's going the other way. So I guess what I would say is either do one way or the other. Either leave them negative like this, or say bx equals 142.9 like that, and by equals 142.9 like that. So one or the other. Make sense? Good.
Excuse me, Professor, could I have a question?
Yes.
Why is the quarter circle is 45 degree?
Oh, because if you look at a quarter circle, right, and you go down here like that, so that's 90 degrees. So that's a right triangle.
Oh, got you. Thank you.
Sure. All right. Any other questions on this one? Okay, let's go back to PowerPoint. Okay, here's another frame problem. Now, I think I might come back to this one because I want to do I want to show you a machine problem just so you can see it. But actually, let's work through this one because we're kind of in that mode. We can do a machine next week with friction, but this one, this problem here, I would say is fairly straightforward. And actually, what I can do is let's do it this way. So let me go ahead and draw it real quick.
So here we have the problem. So what I would say is the first thing, while I'm drawing it real quick, is think about how you're going to solve this. So one of the things you'll notice that when you're drawing out your free body diagram for this is that I is on rollers. So you can determine what the value of I is. And since we're trying to find IGCA, then that would probably make the most steps. So while I'm drawing this, go ahead and calculate what the I reaction is. So it's pretty quick. Anyone get a value? So we know that this is 40 and this is 20, 10, 10, 20, and 48. So we want to find basically this whole thing. So we're looking at this here. So we know that we have this, okay, and we know we have this. Call that a BA. We'll just call it BA. All right, and then we have this down here. And as far as the rest of it goes, something like that. Okay. Now, how did I know what I had there? So that's one of the things in identifying the frames. How did I know? So this is the free body for this piece here, this A, C, G, and I. All right. So I knew I was vertical because the drawing had rollers, right? So that's pretty straightforward. What can we say about this member, and this member? What are those? Those are two force members. All right. So hopefully you saw that. If you didn't, that's something you want to be able to identify. Now, why are they two force members? Because they're contacted in only two places, right? So this one and this one, this one, this one, they're all just connected. That, and that. Now you might be fooled because this has 1, 2, 3, but when you think about this piece here on this side, it doesn't have anything. All right. So this has to be a 2 force, this has to be a 2 force, that has to be a 2 force. So that greatly simplifies the problem because your free body then ends up looking like this. You know the direction of this, and this turns out to be, if you think about 20 and 48, then if you divide this by 4, that's 12, 5, and that's 5. So this ends up being a 5, 12, 13 triangle. Okay. So if we're going to go ahead and solve for that, then first we can sum the moments about H to 0. If we do that, we get IY times 48 minus 40 pounds, because that's our applied force. We have 40 pounds applied at D, remember? And then that's going to be times the distance of what? Of 30 inches. Because we're told it's halfway between. So 20 and 10. And that equals 0. So we end up with IY equal to 25 pounds. So IY, sorry, I'm jumping around, 25 pounds. So IY is 25 pounds, nothing else. All right. So a couple
I
things
have a
we
quick question.
Yes.
Why isn't FG and BC zero force members?
I'm sorry.
Why aren't FG and BC zero force members? Because on the right side they're connected with two um lines in the same direction, or two members in the same direction, and then
Right. And in frames, you don't have zero force members in general. That's a very good question. In trusses, you do, mainly because in trusses, they're the way that they're structured and put together. That's a good question. You won't see zero. You generally don't see zero force members in frames. So I guess how do you differentiate then? If you think about, for one is, well, for one is that you can go through and you can solve and find these values. But I don't have a good answer for you on that one. I'm sorry. I don't. It's just something that's just always been. Trusses have zero force members because of the way they're put together. Frames don't. I'll have to think about that and get back to you, because off the top of my head, I don't know a good reason for that. But getting let's finish this one real quick. But so we have our FG, and so we've identified the forces we have. We have C and we have G, we have I, and then we have BA. And so if we sum the moments about G, this point here, then that will allow us to solve for C, and it allows us to solve for C, and that's right. Because first we need AB. How do we get AB? Oh, that's right. Yeah, we can get now. I'm sorry, I'm getting ahead of myself. Because we have the 25 pounds, now we can get AB, right? Because we know that AB is a two force member going this way, and that's the only vertical component. So if we sum the forces in the Y, then we get essentially -5/13 AB plus 25 equals 0. Now, what I did is, even though I have AB pointing up there, because I saw the 25 pounds was pointing up, I put a negative in front of this, because I know that in order for this to balance, this has to be going the other way. So therefore, AB ends up being 65 pounds. So I know that AB is 65 pounds, basically going down like that, in that direction, for a 5, 12, 13 triangle. So now if I sum the moments about G to 0, we get -C times 20. And that's just the distance there, because I pointed C to the right, and this is 20, this is 20, and this is 20. And then the only other thing I have, since I'm doing about G, is that. And since I know that, I can solve for C. So then that's going to be plus 12/13, because we know that it's going this way. So that's the 12/13 side of AB times AB, and then that's going to be times a distance of 40, and that equals 0. So we plug the 65 into there, and we get C equal to 120 pounds. All right. And then lastly, some of the forces in the X, that allows us to get G. So if we do that, we get 120, because that's our C value. So C, and then minus 5/13 AB, and then plus G equals 0. So 125 minus 5/13 of 65, sorry, plus G equals 0. And so G ends up being, in this context, -60 pounds, or G equals 60 going that direction. All right. So we have, this is 120, and this is going that way. And you don't have to change your free body. I'm just doing it here. This is 60. So I guess getting back to the answer of how do you know it's not a zero force member, I guess, well, for one is when you do these calculations, you end up with a value for each of these. And so the fact that you didn't end up with zero means they can't be a zero force member. But the idea of that is interesting though. I can see where that would be a question. So I'll think about that. Try to get back to you on that one because no one's ever asked me that before. Okay, let's see. With now, I've talked about frames. Now, obviously, in this live lecture, I haven't really talked about any of the theory. There's really, as you can tell from looking at this chapter, there really isn't a lot of theory per se. We're pretty much just applying the concepts that we already have learned in the past to new types of problems. So don't be intimidated if you see weird shapes and whatnot, because they're essentially, there's nothing new to do in terms of application. So this is a good example. This looks intimidating, but this is a toggle clamp. And so you push down at P, and what you're trying to do is you're exerting a force at E to hold a piece of wood or whatever down on a table. So let's just look at the problem before we even do anything, just because some of this I find, and depending on your background and what you've done, how much mechanical type stuff you've done in your life, it can help you. But even if you haven't, it's good to start to visualize what's actually happening in these problems instead of just kind of blindly solving for numbers, because it'll give you a better sense of what's real and what isn't if you get a weird answer. But if you think about this, you have this one piece that's connected at D, and then it's connected at C, and then there's a force applied at P. So you have this long handle. Now, does everyone see that CB is a two force member? So hopefully that stuck out at you right away. So if that's the case, then with the two force member, then you should be able to solve for CB simply by summing moments about D, right? And so if you sum the moments about D, then you can solve for whatever CB is. Now, once you solve for CB, you know its direction, and it's at 45 degrees. You can see that because the distance vertical and horizontal is 12 millimeters. Okay. So knowing that, you know that whatever the value is for CB, you're going to have the same value in the X and in the Y. Then you can sum the forces in the X and the Y, and that will allow you to find the reactions at D. So let's look at that problem. Let's look at how the solution was. And then, so let me go, let's first start that first part. So here we have, our drawing. So we have 160 millimeters between here and here, and there's D and C. Okay, so here's a closer up of that. So there's 5 millimeters height-wise of D, and the distance is 16 between there, and then we know this is 1 to 1. Okay, so if we sum our moments about D, then we know there's a 400 Newton force here. We know it's essentially negative 400 Newtons because it's clockwise times 0.16, because that's 160 millimeters. And then we just break our CB into its two components. So one component is the side that's going up is actually, I'm sorry, the side that has the 5 distance is actually going clockwise also, because you can see if it's going up, that means it's going this way. So it wants to go around. The other part of it is opposing it. So part of this is going clockwise, which is this, and part of it is going counterclockwise, which is this, but it has a greater moment arm, so it's going to be the dominant. And so once we solve, we end up with CB has this huge force in it, 8,228 Newtons. And now what we can do is we can then sum in the x and the y. And what we find is that dx and dy are almost the same. The only difference is that 400 newtons. So dy is 5418, dx is 5818. So there's what we have. Okay. So we know our values for dy and dx. Now, one thing is it's important is to recognize the directions. And so this is, again, where frames come, kind of the idea of frames come back, is you'll notice that when I drew these up here, I drew this to the right and up. And I just did that out of convention. Now, when I look at my answer here, dx is going to the right, which makes sense because CB is going to the left, but dy is going down, okay? And so because dy is going down and to the right on this piece, when we transfer d to this other piece, we have to reverse that, okay? Because then if we put this back together with this, they cancel. And so that's an important thing to remember. So we've identified which directions these are. So now when we put them here, we know this is on this component, the reaction of D on this component is to the left and up. Okay. So that's try to recognize that when you're taking these things apart. So that then the problem becomes fairly easy because D vertical goes right through A. So now we can just sum the moments about A, and all we have is D horizontal, and we know that value. So dx times 12 minus E times 80 equals 0. So if we plug in the 5818 times 12 equals E over 80. And, we could, up here, I could have converted or not converted. It would have came out the same either way. So whether you convert to millimeters or meters doesn't matter if you're just doing moments. So we end up with E equals 872 newtons. So not a huge force increase, barely double. So, but then that makes sense because if you look at this original structure, the moment arm wasn't that much different, right? So what I mean by that is if we look at this, you can see that you have 160 millimeters, you have 80. So it makes sense that if you put in half the force, and that's about half the distance, then you're going to get about double. So that's about right. That makes sense. Any questions on that? Okay. All right. Well, for the quiz this week, I think I mentioned it. The quiz will cover quiz number 6 will cover trusses, zero force members. Okay, so we still have 3 quizzes left. So we have, if we go back to the beginning, trusses and zero force members will be the quiz on Wednesday. Next week's quiz will be frames and machines. And then last quiz, week 10, will be friction. Okay. All right, we're about out of time. Any questions? Any last minute questions? All right. Well, thank you guys for coming. I'll see you in office hours.
Thank you.
You're welcome.